Hello and welcome back to another Calculus 3 multivariable calculus video. Today we're going to be going over surface integrals. What is a surface integral? Well, first off, so to speak, it's a 3D evolution of a line integral, something that we just learned a little bit ago. What it is, well, we're in a line integral, what we were doing prior, added up values along a curvy path. The surface integral is now going to sum values over a curved surface in space. So we're going to be encountering two main types of surface integrals. We're going to be encountering scalar surface integrals and vector surface integrals. And both of these calculate very different things, but I guess getting into the why, well, why are we doing surface integrals? A large application is going to be surface area for scalar surface integrals, and perhaps that's intuitive to us. It's kind of in the name that we're going to be doing surface area. Another application that we're going to be doing is, well, it's the same one that we've been doing for pretty much all the units in Calculus 3 when we can do mass. So if we were given a density of some kind of sheet of whatever, and we were given the mass density, then we're going to be able to calculate the mass with our scalar surface integrals. And as for the large application that we're going to be doing here, it's going to be vector surface integrals with flux. What flux is, it's essentially how much a vector field is passing through a surface. So this is going to be a large application with water flow or anything of that sort of manner of a vector field. Well, flux is going to be measuring how much is passing through essentially. How are we going to do it? Well, once again, similarly to line integrals, we're going to have two different formulas. One for scalar surface integrals, and the other is going to be for vector surface integrals. Notice that, once again, there are some slight differences here, but procedurally, we're going to be going about these the exact same way that we went about scalar and vector line integrals, wherein we use our acronym there. We're going to be parameterizing first, and then our second step is going to be the integrand, our third is going to be calculating our differential, and our fourth is going to be integrating the actual finished product there. So as you can see, I guess pointing out some differences between the scalar and the vector forms here, I guess mainly the biggest difference is that, well, we're going to have a scalar function in our integrand compared to our vector. We're going to have some kind of vector field in our vector form of surface integrals. And there's going to actually be a dot product of a cross product. Once again, I'm going to get into that a little bit more later on, but in the differential, we're going to be taking a cross product of some kind of R sub u cross R sub v. And if we recall earlier, it's essentially going to be a stretch factor. Like we were talking about with Jacobians when we were talking earlier on in Calculus 3. So I guess without further ado, let's go ahead and get into some of the main differences between surface integrals and line integrals. So going in the order of our acronym there, we're going to be talking about parameterizing these surface integrals first. On a pretty easy explanation there, we're really just going to be using conversion formulas, and what that means is we've had conversion formulas in the past for, cylindrical and spherical coordinates. We're pretty much going to be using those in order to parameterize our surfaces now, since we are no longer just doing simple lines. We're actually going to be making surfaces in space now, therefore we're going to need to parameterize according to that. There's a couple of shapes we're going to be running into when parameterizing these surfaces, and you can kind of clump up them together, actually. So the first one we're going to be running into is going to be circular cylinders. We're really just going to be converting to cylindrical coordinates there, so I guess recall that our x is going to equal r cosine of theta, our y is going to equal r sine of theta, and our z is going to equal z. As for the bounds on our parameters are, first of all, they're going to be theta and z. So for the bounds, our theta, well, we know that theta goes from 0 to 2 pi, therefore those are going to be our bounds. And as for z, well, it can go as far as negative infinity to infinity, realistically. So those are kind of the bounds on our parameters there for circular cylinders. Secondly, we're going to be running into circular cones. Similarly to circular cylinders, we're actually going to be turning these into cylindrical coordinates. So once again, we're going to have x is equal to r cosine of theta, y is equal to r sine theta, and our z is actually going to be equal to r this time. Our bounds on our parameters, so our parameters are going to be r and theta, and our bounds on theta, well, we already decided that they are going to be from 0 to 2 pi, that's how far a circle goes, and our r is actually going to be from 0 to infinity. The reason this is because you cannot have a negative r value. It starts at the origin, therefore it's not going to be anything negative. So it's going to range from 0 to infinity there. Third is going to be spheres. Spherical coordinates is what we're going to be converting into. So our x is going to equal rho sine of phi cosine theta, and our y is going to equal rho sine of phi sine theta, and our z is going to equal rho cosine of phi. Note that phi and theta are our parameters now, and that phi, well, that's going to go from the z-axis to the negative z-axis. Therefore, well, what does that area cover there? It's going to be from 0 to pi. And then our theta, once again, we already established that it's going to be a circle, so it's going to go from 0 to 2 pi. And then circular paraboloids are another one, are kind of bowl shape there. We're going to be converting this one into cylindrical as well. Our x is going to be r cosine theta, y is equal to r sine theta, and our z is going to equal r squared. The reason this is because, well, we just need to recall that x squared plus y squared is equal to r squared, and, well, a circular paraboloid function is going to look like z is equal to x squared plus y squared, so just kind of converting it, that's how that pops out there. And similarly, actually, to our circular cone, r and theta are going to be our parameters, and it's actually going to be the exact same bounds. And 5 and 6 are kind of lumped together. They're going to be planes. I didn't write 6 because it's essentially the same concept, but planes, well, we're going to have an explicitly defined function, so our x is going to be equal to x, our y is going to be equal to y, and our z is going to be equal to some plane equation, which is going to look something along the lines of ax plus by plus z. And I just want to note here that x and y are going to be our parameters. And I guess the sixth case is pretty much the exact same parameterization as regular planes. It's just going to look a little bit differently, wherein, you know, we might have a circular cylinder that's cut off by a plane. It doesn't really matter. If there's a plane in it, it's going to be x is equal to x, y is equal to y, and then z is equal to some form of that plane equation. So I guess let's just go ahead and get into a problem that's practicing parameterizing these surface integrals. Our first example, we're asked to parameterize part of z is equal to the square root of 12 minus x squared minus y squared above z is equal to the square root of x squared plus y squared in Cartesian, cylindrical, and spherical coordinates. So this is kind of a hybrid problem here. This is definitely something that you may run into on an exam or some kind of homework when you're asked to parameterize in the 3 coordinate systems that we're aware of. And then from there, you'll be able to pick which one is easiest. But it could definitely be beneficial to kind of practice this way so that you can get a handle on exactly how to parameterize in multiple coordinates. So I guess first off, I already drew the picture here. I guess just kind of notice that, well, our z is equal to the square root of x squared plus y squared. That's the same thing as z squared is equal to x squared plus y squared. And according to our quadric surface unit, that's going to look like cones, right? If we take the square root, it's going to be the positive square root, meaning it's going to be the cone that is above the z-axis, the z is equal to 0 axis. And then as for our z is equal to the square root of 12 minus x squared minus y squared, well, that's just going to be equal, if we do a little bit of algebra there, that's going to be x squared plus y squared plus z squared is equal to 12. And I guess just kind of notice there that that is going to be a sphere. So that's how I kind of drew this picture here. It kind of looks like a snow cone of sorts. So we're going to have to figure out some critical points here so that we can evaluate exactly what we're parameterizing actually. So I guess I kind of took the liberty here of already drawing a little circle on the xy plane there. Well, what that circle is, it's where our two functions are going to intersect, meaning it's the z value that these two intersect. So we already have them explicitly defined as z is equal to square root of 12 minus x squared minus y squared, and z is equal to the square root of x squared plus y squared. So we're just going to go ahead and set those equal to each other, and that should give us our circle equation in the xy plane. So we are going to set square root of 12 minus x squared minus y squared equal to square root of x squared plus y squared. Looks good. That's where our z values intersect there. So let's just go ahead and square both sides. That's going to turn into 12 minus x squared minus y squared is equal to x squared plus y squared. So adding out that x squared plus minus y squared, I guess. So we're going to do plus x squared plus y squared on both sides. So we're going to have 12 is equal to 2x squared plus 2y squared. And then dividing out that 2 there, we're going to have x squared plus y squared is equal to 6. And that 6 is going to be our r squared, meaning our r is actually going to be the square root of 6. So the radius here is going to be the square root of 6 on each side of this circle in the xy plane. There we go. So we kind of found how we're going to solve for our Cartesian coordinates there. So let's just go ahead and do that one. There's going to be more algebra that's going to need to be done when we're doing spherical here, but I guess we'll get to that when we get to that. So when we're doing our Cartesian, let's go ahead and do that in light blue. So our Cartesian coordinates, well, we're pretty much just going to be, well, we have to first of all think of, do we want our bounds on x and y to be, well, let's just, actually, never mind. Let's go ahead and parameterize first, and then we'll decide the bounds. So our x is going to be equal to x, our y is going to be equal to y. And since we're parameterizing the part of z is equal to the square root of 12 minus x squared minus y squared, that means that's what our z is going to be explicitly defined as. So our z is going to be 12 minus x squared minus y squared. Okay, so now we have to evaluate whether or not, do we want our bounds to be dy first, or do we want them to be dx first, because that is going to depend. So regardless of what we choose here, one of the bounds, so I guess our outer bound is going to be from negative square root of 6 to square root of 6, and perhaps that's not too difficult to convince ourselves of. We already did double integrals, therefore we understand how it works. So I'm just going to go ahead and do dy first, actually. So for dy, well, we need to set our little circle there in the xy plane explicitly defined as a function in y. So just kind of rearranging this is going to be y squared is equal to 6 minus x squared. And then taking the square root of both sides, it's going to be y is equal to positive or negative square root of 6 minus x squared. So those are going to be a bounds on y actually there. So we're going to have the negative square root of 6 minus x squared less than or equal to y is less than or equal to 6 minus x squared, the positive square root there. So those are our bounds on our y, and then as I said prior, our x, well, our x is going to be from negative square root of 6 to the square root of 6. So that was our Cartesian coordinates. Let's go ahead and do the second thing we're asked for, which is cylindrical. remember that for our parameterization for cylindrical, our x is going to equal our cosine theta, our y is going to equal our sine of theta. And like I said, we're going to be using this z is equal to square root of 12 minus x squared minus y squared. But I just want to point it out that, well, if we factor out a negative from that square root, well, it's going to turn into the square root of 12 minus x squared plus y squared if we just factor that out. So let me go ahead and write that down real fast. And we'll do it in a different color, just as a note. Square root of 12 minus x squared minus y squared is equal to the square root of 12 minus, in parentheses, x squared plus y squared. And notice that that negative would get multiplied out, therefore these are equivalent terms. And the reason that I did this is because, once again, we're going to need to just know our conversion formulas here. We know that x squared plus y squared is equal to r squared, therefore we can just go ahead and plug that into our cylindrical coordinate. We have z is equal to the square root of 12 minus r squared. For our cylindrical, remember that our r and our theta are going to be what's dependent on. This one should be pretty easy because, you know, this is something that I would definitely do in cylindrical. Well, our radius, our r value, that's going to be the square root of 6. We know that because that's the radius of our circle there. So let's just go ahead and write that down. Our radius, our r, is going to be bounded from 0 to the square root of 6. And since it's a circle in the xy plane, it's going to be going from 0 to 2 pi for our theta bounds. And lastly, let's go ahead and do our spherical coordinates. Let me move this here. Doing our spherical coordinates here. Recall that we have rho sine phi cosine theta, rho sine phi sine theta, and then rho cosine phi. Well, what is our rho going to be? Once again, we're going to have to rearrange our little formula here. So let's just go ahead and make a note. We're going to be parameterizing z is equal to the square root of 12 minus x squared minus y squared. Again there. So let's make a little note. So if we just square that and rearrange it, that's going to be z squared plus y squared plus x squared is equal to 12. And recall that x squared plus y squared plus z squared is going to equal rho squared. Therefore, we have rho squared is equal to 12. Therefore, our rho is equal to the square root of 12. So our rho here in spherical coordinates is actually going to stay constant. Therefore, when we are plugging in our spherical parameterization, we can just go ahead and write that rho as root 12. So our x is actually going to equal the square root of 12 sine of phi cosine of theta. Our y is going to equal square root of 12 sine of phi sine of theta. And our z finally is going to equal the square root of 12 cosine of phi. Phi and theta are our parameters here, and our phi, well, let's go ahead and do our theta first, since that one's pretty easy there. Our theta, it's a circle like I said prior, so it's just going to go from 0 to 2 pi. And now, let's see here. When we're now going to have to set our sphere and our cone equal to each other, convert it to spherical, and then that way we'll be able to figure out what our bounds on phi are. So let's just go ahead and do our math there. Yeah. So in order to solve for that phi value, what we're actually going to be using is we're going to be using that part above z is equal to the square root of x squared plus y squared. And just kind of using our spherical conversions, we're going to have z is equal to, well, first of all, we're going to convert that x squared plus y squared into our cylindrical, so that x squared plus y squared is going to equal r squared. Take the square root of that, we're going to have z is equal to r. And then from there, we can just use our conversions. So we're going to have rho cosine of phi is equal to rho sine of phi. Remember that these rho's are the same. So if we just go ahead and divide out that rho, we're going to have cosine of phi is equal to sine of phi. Or we're going to have tangent of phi is equal to 1, and that occurs at pi over 4, which is our bound on phi right there. So that right there is how you are going to parameterize, and I just want to make it known here that we realistically could have done the algebra with our z is equal to x squared plus y squared square root, or we could have done what I did and did z is equal to the square root of 12 minus x squared minus a y squared, and that's kind of an identity, not an identity, but that's just kind of something that we can keep in mind whenever we're parameterizing two kind of functions, is that we can use either one and we're going to get the exact same parameterizations. It's just a matter of which one is going to be easier. So that kind of solves our question on how we're going to parameterize. That's the first step. Now let's go ahead and talk about our integrand. Well, our integrand, it's going to be the exact same procedure, wherein we're pretty much just going to plug in our parameterized surface into our integrand that's already given there. So that's going to be the exact same. So as for our differential, I actually just went ahead and drew a little picture here of some kind of generalized surface there, and there's a couple of components of this that I kind of want to mention. Wherein, okay, we already have our parameterized surface, so we already did our u and v, so we already have our vector valued function r of uv is going to equal some vector x of uv, y of uv, and z of uv. Well, if we go ahead and we need to take the partial derivatives of each of those, right? So pretty much what we're going to be doing is we're going to have some r sub u that is depicted from our yellow lines there, and then we're actually going to be having our r sub v, which is kind of depicted by our orange lines. So when we're doing this, we're going to have two kind of partial derivatives, and like I said, this is kind of what a partial derivative looks like on a surface. And what these are doing is they're intersecting to make a bunch of kind of parallelograms there. And what that means is, well, we need to find the area of this parallelogram, because the area of the parallelogram is essentially going to give us our Jacobian. If we go ahead and take the magnitude of the r sub u and our r sub v cross product. So I guess just recall that in vector calculus, the magnitude of the cross product of two vectors gives the area of the parallelogram that they span. So our r sub u actually is going to be the orange lines there, the orange partials on our surface, and our r sub v is going to be the yellow lines on our surface. And like I said, they are going to make infinitely small parallelograms, and each of these is going to act as a Jacobian back in our prior unit, wherein we're transforming the flat area du dv into an actually curved area on the surface via that cross product. So that's what our differential is going to be for our scalar surface integrals. And then as for our fourth and final step, integrate, it's essentially going to be the same procedure-ish. Obviously, we're going to have different formulas now. So instead of just having our line integral, we're actually going to have a double integral, or a surface integral in this case they're called. And I'll explain a little bit more in the future on what the difference is between a surface and a double integral. but it's essentially going to be the differential that makes it different. But otherwise, procedurally, we are just going to be integrating, and there's nothing really different about that. First example for our scalar surface integrals is find the surface area of the part of a plane r of uv is equal to the vector 1 plus v, u minus 2v, 3 minus 5u plus v. The bounds on u look to be 0 and 1, and v is going to be from -1 to 1. So the surface area of S is essentially going to be, there's no integrand, or our integrand is actually just going to be equal to 1. So we're pretty much just going to be doing a double integral of our differential. So let's just go ahead and do our 4-step process there, pi di pity. First step is going to be to parameterize our surface, and it looks like that was already done. We were given a parameterized surface. That is going to be our r of uv is equal to 1 plus v, u minus 2v, and 3 minus 5u plus v. 0 is less than or equal to u is less than or equal to 1. And -1 is less than or equal to v is less than or equal to 1. So let's go ahead and move on to step 2, our integrand. Well, our integrand, I just said earlier, that's just going to be equal to 1. So our f of uv is just going to equal 1 as well. There's no variables to plug into anything. Third is going to be our differential. Kind of looking at this right here, well, we're going to have r sub u cross r sub v, which is pretty much just saying we're going to take the partial of our parameterized surface with respect to u and respect to v. We're going to take the cross product of that, and then we're going to take the magnitude of it. So let's just go ahead and do that step by step. Well, what is r sub u? R sub u is going to equal the partial with respect to u of our vector. That is going to be 1 plus v, u minus 2v, and 3 minus 5u plus v. Taking the partial with respect to u of each of our separate components, well, our x component, that's going to be 1 plus v. There's no u in there. Everything is treated as a constant. Therefore, our x component is going to be 0. Our y component is u minus 2v. That v is going to be treated as a constant again, so that's going to be 0. And that u is going to be 1. Finally, for our z component here, we have 3 minus 5u plus v. Taking the partial with respect to u there, that 3 is already a constant, so it's going to be treated as a constant. That negative 5u has that u in there. Using the power rule there, it's just going to be equal to negative 5. And then plus v, well, that v is not u, therefore it's going to be treated as a constant, so that's going to be 0. Meaning our partial of our parameterized surface with respect to u is going to be 0, 1, negative 5. Similarly, the process for our r sub v is going to be the partial with respect to v of our parameterized surface. 1 plus v, u minus 2v, 3 minus 5u plus v. For our x component, that we are going to have 1 plus v. Taking the derivative there, with respect to v, that 1 is going to be a constant, therefore it's 0. And then we're going to be taking the derivative of v with respect to v, that's just going to be 1. For our y component, we're going to have u minus 2v. Taking the partial with respect to v there, that u is going to be treated as a constant, therefore it is going to be 0. And that negative 2v is just going to turn out to be negative 2. And then finally, for our z component, we're going to have 3 minus 5u plus v. And then taking the partial with respect to v there, that 3 is constant, 0, negative 5u treated as a constant, 0, and then plus v, that's going to be 1. So our partial of our parameterized surface with respect to v is going to be 1, negative 2, 1. So now we're going to go ahead and take the cross product here. R sub u cross rv. That is going to be I, j, k. R sub u is going to be 0, 1, negative 5. And our R sub v is going to be 1, negative 2, 1. Make our determinant here. These are all constants, so I'm just going to go ahead and kind of do the math in my head here. For our I component, we're just going to go ahead and skip to bracket notation instead of making many determinants. So our x component is going to be 1 times 1 minus negative 5 times 2, negative 2. So that is going to be 1 minus 10. That's going to be negative 9. For our j component, we're going to have 0 times 1. That's going to be 0 minus negative 5 times 1. That's going to turn out to be 5. But since it is our j component, we are adding an extra negative, so it's going to be negative 5. And as for our k component, that's going to be 0 times negative 2. That's going to be 0 minus 1 times 1, so that's just going to be negative 1. So that is our r sub u cross r sub v. So now let's go ahead and take the magnitude here. Which is going to be the square root of all of these individual components summed and squared. So we are going to have negative 9 squared plus negative 5 squared plus negative 1 squared. 9 squared is going to be 81, 5 squared is going to be 25, 1 squared is going to be 1. 25 plus 1, that's going to be 26. 26 plus 81 is going to be 107. That is going to be our magnitude of our cross product there. And I suppose something that I kind of want to highlight now is when we're doing our differential, for right now, when we're doing scalar surface integrals, it actually doesn't matter the order that we do it in, because in the end, we're going to be taking the magnitude. Therefore, any negative signs that get picked up from flipping this cross product just kind of go away from that square in our magnitude. Therefore, I guess something that we kind of want to note is that we could do r cross r sub u cross r sub v, or we could flip it and it would be the exact same differential. Speaking from scalar surface integrals, and when we're doing vector surface integrals, it's going to be a different story. But for scalar surface integrals, it is interchangeable. Final step here is we're going to evaluate our integral. So we're going to have a double integral from negative 1 to 1 and 0 to 1. And you could flip that. It doesn't really matter. Our bounds are constants. Therefore, it really doesn't matter. We're pretty much just doing it over a square or a rectangle or some kind of shape like that. It's going to be, our integrand is going to be 107. Our integrand is actually 1, and our differential is negative, or square root of 107, but we're going to have du dv. In evaluating this, we're going to have the integral from negative 1 to 1 of the square root of 107 u from 0 to 1 dv, which is going to equal from negative 1 to 1 of square root of 107 dv, which is going to equal square root of 107 v from v is equal to negative 1 to v is equal to 1, which is going to equal the square root of 107 minus negative square root of 107, so that's just going to be plus square root of 107. So that is going to be our final answer. for our pretty basic surface integral here. For our final and hardest example, I would argue, I guess we'll see why, we're going to go ahead and moving on to our second surface integral example for scalar functions. We're asked to evaluate the surface integral of x squared, where s is part of z is equal to square root of x squared plus y squared, with 0 is less than or equal to z is less than or equal to 1. So I already drew this out, took the liberty of drawing that out there. There's a little circle in the xy plane that we're actually going to be using, so I need to find the critical points there. How I'm going to do that is the very upmost of this cone that we have here, z is equal to x squared plus y squared. That's when z is equal to 1. Therefore, x squared plus y squared is equal to 1, so that's pretty much going to be our radius here. That's going to be the function x squared plus y squared is equal to 1. Those are our critical points here. And I guess we can go ahead and get started. So using our acronym, we have PIDI. First, we're going to parameterize. So to parameterize, notice that it may be easiest to actually parameterize in polar. What that means is we're going to have our x is equal to, or cylindrical, I guess. X is going to equal r cosine theta. Y is going to equal r sine of theta. And our z is going to equal the square root of x squared plus y squared. Once again, recall x squared plus y squared is equal to r squared. Therefore, we have z is equal to the square root of r squared. So z is equal to r. And our bounds, well, our r is going to go from 0 to 1. And our theta is going to go from 0 to 2 pi since it is a circle. We are completely parameterized now. Let's go ahead and write it into our vector notation. Our r of r theta may be a little bit confusing there, but just know that that r on the outside is actually our parameterized function. Is equal to r cosine theta, r sine theta, and r. Go ahead and moving on to step 2, we have our integrand. Well, our integrand, as we can see here, is going to be x squared. Therefore, our f of r theta, plugging in that parameterized function we had there, that parameterized surface, that is going to be our cosine theta squared, which we can just go ahead and simplify as r squared cosine squared of theta. Looks like our integrand is done. Let's go ahead and do our differential now. Differential, recall that we are going to have our r sub u cross r sub v, and then we're going to be taking the magnitude of that. And like I said earlier, well, the order when doing scalar surface integrals, it actually doesn't matter, meaning we could do r sub v cross r sub u if we really wanted to. But I'm just going to go down the line here. We're going to have our r sub r, actually, so we're going to be taking the partial derivative of our parameterized surface with respect to r. And our parameterized surface is r cosine theta, r sine theta, r. And taking the partial with respect to r there, we're just going to have that r is going to go away in the x term. So cosine theta. And our second y term, that r is once again going to go away. That's just going to become sine theta. And then the derivative of r with respect to r is going to be 1. So that's our r sub r. Now our r sub theta is going to be the partial of our parameterized surface with respect to theta. R cosine theta, r sine theta, r. Taking the derivative of r cosine theta with respect to theta, well, the r is going to stay the same, but we're pretty much just going to be doing the derivative of cosine theta, and recall that that is going to equal negative r sine theta. Taking the derivative of r sine of theta with respect to theta, we're pretty much just going to be taking the derivative of sine of theta, which is going to be cosine theta. So we are going to have our cosine theta as our y term. And finally, our z term is going to be the derivative of r with respect to theta. Well, that r is just going to be treated as a constant. Therefore, that is going to go to 0. So we have our two terms now. So let's just go ahead and make our determinant. So we're going to have our r sub r cross r sub theta. And let's just go ahead and write down our terms first. So we're going to have cosine theta, sine theta, 1 as our r sub r, negative r sine theta, r cosine theta, and 0 with our I, j, and k on top. Make our little determinant. And let's see. This actually should be simple enough to be able to do in our head. I wouldn't advise this if you're not comfortable with it. Our x component, or our I component, well, that's going to be sine of theta times 0 minus 1 times r cosine theta. So that first term is actually just going to equal 0, so we're just going to have negative r cosine theta. Secondly, for our j term, we're going to have, looks like 3 negatives there, therefore it's going to pop out a negative. So whatever we have, it's going to be negative. We're going to have cosine of theta times 0 minus 1 times negative r sine of theta. So that is actually just going to be 0 plus r sine of theta, and then once again we're going to have that leftover negative, so it's going to be negative r sine of theta. And finally, for our k component, we are going to have cosine theta times r cosine theta minus sine theta times r negative r sine of theta. We'll write this one out all the way so that we can do an identity of perhaps. That is our cross product there. Well, if you notice in our z component or our k component, we can actually just go ahead and factor out that r. We're going to have cosine squared of theta plus sine squared of theta, meaning we are going to be able to just cross that out and equal it to 1. Recall that sine squared of theta plus cosine squared of theta is equal to 1. Therefore, our final cross product is going to be negative r cosine theta, negative r sine theta, and r. Now, final step here for our differential is we're going to be taking the magnitude of this. So our magnitude of r sub r cross r theta, r sub theta, is going to equal the square root of negative r cosine theta squared plus negative r sine theta squared plus r squared. Just go ahead and showing the work here. We're going to have the square root of r squared cosine theta, cosine squared theta, excuse me, plus r squared sine squared theta plus r squared. Once again, we're going to go ahead and factor out that r squared in this term right here. So this is just going to be equal to r squared times cosine squared of theta plus sine squared of theta. Go ahead and use that identity that we just used. That's just going to be equal to r squared times 1. So this is just going to be equal to the square root of r squared plus r squared, which is going to be 2r squared. That is going to be our final differential. And finally, we are going to set up our integral. Fourth step is going to be integrate. Oops. Well, we are going to have the double integral from 0 to 2 pi, from 0 to 1, of our integrand, which was r squared cosine theta, cosine squared theta, times our differential, which was square root of 2r squared, dr d theta. and that is going to be our fourth and final step. We will just be setting it up and not evaluating. So I just kind of want to make a note here. We can just see here that, this double integral is in polar now. A question that we may be having here is, and I just want to address it now, is, what happens to the r dr d theta? So the Jacobian, what happens there? Well, to put it simply, if we start in the proper coordinate system, so our first step, parameterizing, if we start in the proper coordinate system, then the Jacobian is not necessary. So therefore, that r dr d theta that we're used to when we translate our Cartesian coordinates to our polar coordinates in double integrals, we don't need that r dr d theta. We only need this differential dr d theta. So essentially what I'm saying is that this differential kind of acts as the Jacobian for this double integral, for this change of coordinate systems. Let's go ahead and get into another example. So we're actually going to be transitioning away from scalar surface integrals and into vector surface integrals, and this is a pretty good example for doing that. Our example says we are given a vector field 0, 0, -1 that represents rainfall. Our surface is z is equal to 4 minus 2x minus y in octet 1, and it represents a roof. We're finding the downward flux here. And I just want to recall here that, what is flux exactly calculating? Flux is going to be, it's going to be how much of our vector field is passing through a surface. So what it means is how much of this rainfall is hitting the roof. So something that could be beneficial whenever we are doing surface integrals in the vector form is actually drawing our vector field a little bit. In a lot of cases, it's a little bit difficult to do, but for something like this, 0, 0, -1, it's just going to be pointing downward with a magnitude of 1 everywhere around, right? So I'm just going to go ahead and draw our little rainfall here. And this rain right here kind of represents our vector field, our rainfall in this application. So let's just go ahead and get into solving this actually. First, we're going to parameterize. Using our acronym, PITY. First, we're going to parameterize. Something I want to make note of is, our surface is an explicitly defined function, meaning we can just set our x equal to x, our y equal to y, and our z is actually going to be our surface. And our z is equal to 4 minus 2x minus y. So kind of squishing this image down, or perhaps looking at it from above into the xy plane, we kind of just have like a triangle in the xy plane. Let me do this in a different color actually. We're going to have essentially a triangle in the xy plane here. So how we're going to find that kind of function that relates to in the xy plane is we're going to be taking the xy trace. And I just kind of want to remember that, recall that the xy trace is when we're setting our z equal to 0 and solving, right? So this function right here is going to be when z is equal to 0, this is going to be our xy trace, like I said. So we're going to have 0 is equal to 4 minus 2x minus y. So then our y is just going to equal 4 minus 2x. So therefore, when we are taking our y, our bounds on y, we're in the first octant, meaning we're bounded by y is equal to 0, and then that is going to go from y 0 to 4 minus 2x. And for our x, we're once again bounded in the first octant, meaning our lower bound is going to be 0 for our x, and then our upper bound is just going to be this 2 value right there. That is the x-intercept. So we parameterize there. Let's go ahead and do our Integrand now, step 2. R of xy is going to equal xy. Sorry, I skipped a little step there. 4 minus 2x minus y. Okay, our integrand. Well, our integrand, we're not really given an integrand other than, or not an integrand with any variables in it to swap in. Our integrand in this case is actually just going to be our vector field. That's going to be our rainfall. So our f is just going to stay the exact same. It's constant, or there's scalar. It's not any variables in there, so it's just going to be 0, 0, -1. And then for number 3, it's going to be our differential. So I guess let's just go ahead and scroll all the way up and return to our vector. What our differential is going to be, well, we already solved for our bounds. We did our parameterization step. We already solved for our integrand. That was just going to 0, 0, -1. Now our differential is going to be this r sub u cross r sub v. And notice we are not taking the magnitude of this. It's actually going to be dot product with our integrand. So let's just go ahead and do r sub u cross r sub v. In this case, it's actually going to be r sub x cross r sub y. Well, our r sub x is going to equal the partial of our parameterized surface, x, y, 4 minus 2x minus y. The partial with respect to x here is going to be, our x component is going to be the partial of x with respect to x, so that's going to be 1. Our y component is going to be the partial of y with respect to y. That's going to be 0, or with respect to x, apologize. And then our z component is going to be the partial of 4 minus 2x minus y with respect to x. That is going to be -2. That 4 is treated as a constant. That -2x, that was what we kind of solved for. And then this -y is going to be treated as a constant as well. Now our s sub y is going to be the partial with respect to y of this parameterized surface. Partial with respect to y of x is going to be 0. Partial of y with respect to y is going to be 1. And the partial of 4 minus 2x minus y is going to, with respect to y, is going to equal -1. Once again, note that 4 is constant, it's going to be 0. And that -2 is treated as a constant because we are integrating with, or differentiating with respect to y. So it's going to be -1. Now we are going to just take the cross product of these two, r sub x cross r sub y. This is going to be 1, 0, -2, 0, 1, -1, I, j, and k. Once again, pretty simple one that we can do in our head, actually, if you're comfortable, of course. Well, for our I component, we're going to have 0 times -1 minus -2 times 1. So that's going to be 0 minus -2, which is going to be 2. For our j component, we're going to have 1 times -1 minus -2 times 0. So that's just going to be 1 times -1. Remember that j component picks up a negative, therefore we are going to have a -1, which is going to be 1. And our k component is going to be 1 times 1 minus 0 times 0, which is just going to be 1. So that is our r sub x cross r sub y. And I guess when I was talking about scalar surface integrals, I was talking about how the differential order doesn't actually matter. It was interchangeable because at the end, well, we would take the magnitude and that just kind of got rid of any negative signs that we might have picked up. So that means that we could flip our cross product order if we really wanted to. Now the same does not actually apply when we're doing vector surface integrals, and the reason is there are different directions of flux, right? So flux is a vector. It's a vector value. Therefore, not the flux is not a vector value, sorry, but our differential is vector value now. Therefore, when we're finding upward, downward, inward, outward flux, the direction of that is going to matter. And I'll get more into this in just a little bit here, but when we're finding the downward flux, that means that we need to look at our z value here. Our z value is 1. And I guess it sort of depends on what you define downward as, I suppose, if you really wanted to flip your coordinate axis, but obviously downward is going to be down and upward is going to be up. So when we have a positive 1 in our z value, that's going to be our upward flux. So if we were to use this r sub x cross r sub y, well, we would actually be calculating the upward flux of our rainfall onto our roof, meaning what we would probably, I guess the best application of that would be how much rain bounces up when it hits the roof. I guess that would be, rather than how much rain is actually hitting our roof. So this just kind of brings in a really important point when we're calculating our differential, which is we really need to be kind of picky about what flux we're calculating here, because like I said, downward is going to be different from upward, equally inward is going to be different from outward flux. So what is all this to say? All this is to say, well, our z value is upward flux and we want downward flux, therefore we're just going to have to negate our differential. And how we're going to do that is just go ahead and we just need to remember our vector calculus kind of identity here, wherein we have our r sub x cross r sub y. Well, if we negate that, that's just going to be equal to r sub y cross r sub x. So pretty much what I mean to say is that it's not the orientation of your cross product matters whenever we're doing vector surface integrals, especially when it's specifying what kind of flux it wants us to calculate here. So when we're doing our differential, we're actually technically going to be doing r sub y cross r sub x. So now that we have that, well, we're just going to need to negate this, meaning our actual flux, or our actual differential, is going to be r sub y cross r sub x, meaning we're just going to negate the whole thing. So we have -2, -1, -1. And our kind of little sanity check is, well, downward flux, meaning roughly meaning in this scenario that our z value must be negative, and in this differential now, well, our z value is -1, meaning it does conform to the kind of flux that we want. At the very end, step 4 is going to be our integral itself. So our downward flux is going to equal the surface integral of our integrand 0, 0, -1 dotted with our differential, which is -2, -1, -1. And then we decided our order is going to be dy dx by bounding our y in terms of x. I suppose a little double integral sanity check here that we kind of checked for a while ago is, well, if we did do dx dy and we didn't flip our bounds, then we would have an unsolvable integral wherein instead of an actual value popping out, it would pop out something with variables in it, which is not possible when we're doing definite integrals. Then our x was bounded from 0 to 2. So going ahead and evaluating this, looks like a pretty easy one to evaluate. We're going to have the integral from 0 to 2 and the integral from 0 to 4 minus 2x of the dot product between these two. The first term is going to be 0 times -2. That's going to be 0. Our second term is going to be 0 times -1. That's going to be 0. And then our final term is going to be -1 times -1, which is going to be 1. So our integrand is going to be 1 dy dx. We're going to have the integral from 0 to 2 of y from y is equal to 0 and y is equal to 4 minus 2x dx. The integral from 0 to 2 of 4 minus 2x dx, which is going to be the integral of 4x minus x squared from 0 to 2, which is going to equal 4 times 8, or 4 times 2, that's 8, and then minus 2 squared, which is 4, and then all that first term is going to be subtracted by our second term, which is going to be 4 times 0 minus 0, which is just going to be 0. Therefore, our downward flux is going to be 4. So I guess there's another note that I kind of wanted to make in the differential, which is when we have an explicitly defined function, we can actually conveniently take a shortcut here. And I guess take it with a grain of salt, because this is only happens when, once again, when we have an explicitly defined function. So that what that means is we're going to have our parameters be x is equal to x, y is equal to y, and then z is equal to some kind of function. Typically it's going to be a plane, but not always. When you have something like that, so once again an explicitly defined function wherein our z is a function in x and y in the xy plane, then we can kind of make a shortcut here. So instead of calculating our differential by doing our partials of our parameterized surface with respect to x and with respect to y and taking the cross product, what we can actually do is, when there is an explicitly defined surface, our r sub x cross r sub y actually is going to equal the negative partial of our z function, z of xy, I suppose, well, g of xy. The negative of our g of xy with respect to the negative partial of our g of xy with respect to y, and then that will be 1. And this does always work whenever we have an explicitly defined function, so I guess kind of what that g of xy is, well, that's our explicitly defined functions, so that's going to be that z is equal to 4 minus 2x minus y, and let's just go ahead and prove that there. If we were to use this shortcut, well, we would have the negative partial with respect to x of 4 minus 2x minus y, that would be negative 2. So then our negative partial of that would be positive 2. And then similarly, our negative partial with respect to y of 4 minus 2x minus y is going to be negative 1, which would be 1. And then our z component would just be 1 right there. So as you can see, 2, 1, 1, so the explicitly defined kind of shortcut that we use there is the exact same product that we got out of our differential. So it could be definitely a helpful shortcut if you're willing to memorize it. If you're not, then the solving the partials and taking the cross product is a perfectly acceptable way. Just once again recall that we need to factor in that orientation of our flux there. So I guess that brings me to my note here. Nothing more to talk about that example, but the big note, so one of the big reasons why that problem was the way it was is because the orientation of the flux matters. So there's going to be different wording here. We're going to have upward flux, we're going to have downward flux, we're going to have inward flux, and we're going to have outward flux. So with this little surface right here, I kind of demonstrated what all those are going to look like. Well, that downward flux is going to be some kind of vector pointing downward, obviously. And then the outward flux is going to be an arrow, so that kind of vector pointing outside of the surface. That inward, depicted in green, is going to be, well, inward. It's going to be pointing in toward the center of our surface. And then finally, our upward flux is going to be pointing up out of our surface. So kind of color-coded fluxes there, I guess I could say. Then the orientation of the flux really does matter whenever we're doing this. So I guess the moral of the story is whenever you are solving a problem, you're definitely going to want to take into account what kind of flux it's asking for, because that is going to matter in our final answer. In our next example, we are asked to find outward flux of our vector field x, y, e to the negative z through x squared plus y squared is equal to 4, with 1 is less than or equal to z is less than or equal to 5. I took the liberty here of actually drawing this cylinder that we already have. So the xy plane, well, it kind of gives us that equation. That's going to be x squared plus y squared is equal to 4. That little shadow, you could almost think of it as, or, squishing this shape down into the xy plane, or looking at it from the z-axis, whatever kind of metaphor you want to use. In the xy plane, it's going to look like a circle with a radius of 2. So we have a circle of radius 2. I believe that's really all we need in order to compute this. So let's just go ahead and parameterize. I suppose just note that, we have a cylinder here. There's kind of a technique named after it, and we're going to be using cylindrical coordinates. Well, our radius is going to stay constant throughout this, meaning we're actually going to have our bounds, our parameters are going to be theta and z. But let's just go ahead and convert this first. We're going to have x is equal to r cosine theta, but our r is going to be 2 all the way around, 2 cosine theta. Our y is going to equal 2 sine theta, and our z is going to equal z. Our theta is going to go from 0 to 2 pi, and our z was given to us to go from 1 to 5. So that is our parameterized surface. Let's just go ahead and write it down though. R of theta z is going to equal 2 cosine theta, 2 sine theta, z. Moving on to our second step here, our integrand. Well, what was our vector field given to us? Our vector field was x, y, e to the z. So our f of x, y, z is equal to x, y, e to the z. Therefore, our f of r of theta z is going to equal 2 cosine theta for our x component. Our y component is going to be 2 sine theta. And our z component is going to stay the exact same. It's going to be e to the z. Next step is going to be our differential. Like I said, I just made that note about how the orientation of the flux matters. So we're going to go ahead and be careful here about what orientation we choose. So what goes first in our cross product. Obviously, we can't predict what our cross product is going to turn out to be right now. But let's just go ahead and compute it one way, and then worst case, we're going to have to negate. So moving on to our differential, well, we're going to be doing our theta cross our z. So let's just go ahead and compute the individual parts of it. Our r sub theta is going to equal our partial with respect to theta of our parameterized surface. That is going to be 2 cosine theta, 2 sine theta, z. This is going to equal, well, we have the derivative of 2 cosine theta with respect to theta is going to be negative 2 sine theta. Similarly, the derivative of 2 sine theta with respect to theta is going to be 2 cosine theta. And then the derivative of z with respect to theta is obviously going to be 0. Now computing our r sub z, which is going to be notationally, is just going to be the partial with respect to z of our 2 cosine theta, our parameterized surface, 2 sine theta z. And pretty simply here, well, we don't have a z variable in any component other than our k component of our vector. Therefore, it's just going to be 0, 0, and then what's the partial of z with respect to z? It's just going to be 1. So now, kind of taking our cross product here, we're going to have r theta cross r z. Let's go ahead and write down our r theta first so that we can kind of space this properly. 2 cosine theta 0, 0, 0, 1. And we're going to have our I, j, k. Make a determinant here. Alrighty. We're going to skip steps here, doing the determinant in the head again. For our I component, we're going to have 2 cosine theta times 1 minus 0, so that's just going to be 2 cosine theta. For our j component, we're going to have negative 2 sine theta times 1 minus 0. We're going to pick up another negative there, therefore this is going to actually be 2 sine theta. And finally, for our k component, we're going to have negative 2 times 0, negative 2 sine theta times 0, minus 2 cosine theta times 0, which is just going to be 0. So now that we did our cross product, our differential, so let's just go ahead and make sure that notationally this is proper. We are asked to find the outward flux, I believe. Yep, we're asked to find the outward flux, meaning we want our vectors to be pointing outward, whatever our differential is, right? So how are we going to do this? How do we find this? Well, we just kind of need to think of in our head what this vector looks like. Purely based off signs, not really, the functions themselves don't matter that much, to tell you the truth. So we're pretty much just looking for the signs. So really, we're just going to have a positive 0, meaning in an xy plane, we're going to be looking like this pretty much everywhere. So it is going to be radial. So kind of drawing that vector field two-dimensionally, we can kind of visualize it perhaps that, well, that outward flux actually conforms to our differential, meaning our differential is oriented properly. Notice if I, for some reason, did r sub z cross r sub theta, then we would have this answer right here just negated, and that would actually be inward flux. So looks like we actually computed our differential properly, so let's just go ahead and finish it off with our integral. Looks like this is going to be a long one, so we're going to take up some space here. We're going to have the double integral from 0 to 2 pi, and then I believe it was 1 to 5. Let me check. 1 to 5 for our z. And we're going to do our integrand, 2 cosine theta, 2 sine theta, z, e to the z, right? E to the z. Crossed with our differential, which is 2 cosine theta, 2 sine theta, 0. And then that is going to be dz d theta. Expanding this is going to be from 0 to 2 pi, and then 1 to 5, 4 cosine squared of theta, plus 4 sine squared of theta, plus 0. So that's just going to be that, dz d theta. And notice that if we factor out that 4, we're going to have cosine squared of theta plus sine squared of theta, which would equal 1. Therefore, this is just equal to 0 to 2 pi, 1 to 5 of 4 dz d theta. Kind of doing a step in my head, this is going to be 4z evaluated from z is equal to 5 and z is equal to 1. So we're going to have 20 minus 4, which is going to equal 16. So we're going to have 0 to 2 pi of 16 d theta, which is going to equal 32 pi. And that is the outward flux of our vector field through x squared plus y squared is equal to 4, with 1 is less than or equal to 0, z is less than or equal to 5. So for our final harder example here, we're going to be asked to calculate the outward flux of our vector field x, y, z through x squared plus y squared plus z squared is equal to 1. Set up, do not evaluate. So for this one, it's actually really not needed to draw a picture, although you can. I would argue that it's really not needed. We just know that this is a sphere right there, and that outward flux, well, we're not really going to be drawing that vector field. It's just going to be a sphere that our surface is over. So our first step here is going to parameterize. Well, if we have a sphere, then that should ring a bell. We're really going to want to use our spherical coordinates here. Just recall that our x is equal to rho sine theta or sine phi cosine theta. Y is equal to rho sine phi sine theta. And then RZ is equal to rho cosine phi. And since our rho squared, well, we know x squared plus y squared plus z squared is equal to 1, therefore our rho squared is equal to 1, therefore our rho is equal to 1. Our rho is constant, meaning our parameters are going to be phi and theta. So we're going to have sine phi cosine theta, sine phi sine theta, and then finally cosine phi. And then our bounds on phi are going to be from 0 to pi. It is the entire sphere. And then our bounds on theta are going to be a circle, 2 pi. So that's parameterized. Let's go ahead and do our integrand now. Well, our integrand, our vector field is f of x, y, z is equal to, I believe it was x, y, z. Yep. So our f of r of phi theta is going to equal, well, just these individual components here. Let me write it out. I keep forgetting to do that. I apologize. Sine phi cosine theta, sine phi sine theta, and cosine phi. It's actually just going to look like it's going to be the exact same thing as our parameterized surface. Once again, just observe that, our x component of our parameterized surface goes into our x value, y value of our parameterized surface goes into our y for our vector field, and so on and so forth with our z. Sine phi sine theta. And finally, cosine phi. Third step, we're going to be doing our differential. This is really the reason that I kind of label this as a more difficult problem, because it's really easy to make an algebraic mistake here. So we're going to be doing our phi cross r theta. Well, our r sub phi is going to equal the partial of our parameterized surface with respect to phi. That is sine phi cosine theta, sine phi sine theta, and cosine phi. Well, the partial of sine phi cosine theta with respect to phi is going to be, that's going to be cosine phi cosine theta. We're pretty much just ignoring the sine theta cosine thetas. Similarly, actually, the partial of sine phi sine theta with respect to phi is going to be cosine phi sine theta. And finally, the derivative of cosine phi with respect to phi is going to be negative sine phi. That is our r sub phi. Now our r sub theta is going to be the partial of, with respect to theta, of our vector field. I'm just going to go ahead and copy and paste this. Alrighty. Well, the partial derivative of sine phi cosine theta with respect to theta is just going to be negative sine phi sine theta. Similarly, the partial of sine phi sine theta with respect to theta is going to be sine phi cosine theta. And finally, there is no theta within our k component, so therefore it's just going to be 0 there. Now taking the cross product, r sub phi cross r theta, this one we're definitely going to want to write out our terms before we try to space anything out. Starting off with our r sub phi, we're going to have cosine of phi, cosine theta. We're going to have cosine phi, sine theta. we're going to have negative sine of phi. And then our r sub theta is going to be negative sine of phi sine theta, sine of phi cosine theta, and 0. We're going to have that I, j, and k components. Make our little determinant here. And like I said, we are not, this is complicated enough that even I don't want to do this in my head. Not saying I'm the greatest of all time at determinants, but when we're having multiple different variables here multiplying, I definitely want to make sure I don't make a mistake. So for our I component, we're going to be doing cosine phi sine theta times 0 minus sine phi minus sine phi times sine phi cosine theta. So looks like that kind of negative right there negates, meaning it's just going to turn positive. So we're going to have sine squared of phi cosine theta. I guess I am already doing it in my head. Whatever. That's okay. That cosine phi cosine theta times 0 is going to be 0. So we're going to subtract that. We're going to do 0 minus negative sine of phi times the negative sine of phi sine theta. That's 4 negatives, so it's going to cancel out. I might as well just ditch the determinants. Why not? I already started doing it in my head. That's 4 negatives, therefore it's going to go ahead and be positive there. Sine squared of phi sine theta. And then finally our k component, this is the one that might be difficult. We're going to have sine of phi cosine phi, and then it looks like that's going to be cosine squared of theta minus negative, so then that's going to be positive, sine phi cosine phi sine squared of theta. Sine squared of theta. That is going to be our cross product there. Let me see here. What can I do? What can I simplify? I can simplify this actually. I guess just kind of notice that I can pull out that common sine phi cosine phi. And then this is just going to be cosine squared of theta plus sine squared of theta. Our favorite identity, I guess. This is going to be 1. Therefore, our final cross product is going to be sine squared of phi cosine theta, sine squared of phi sine theta, and sine phi cosine phi. So now going ahead and integrating, not really integrating, we're just asked to set it up here. Our bounds here are going to be from, let me see, which order do I think we'll do d phi d theta. So we're going to have from 0 to pi, and then 0 to 2 pi. And then we are going to have our integrand. I'm just going to copy and paste now, to be honest. I think that would definitely be the easiest way to go about this, instead of having to rewrite all this. Oops. Copy and paste our integrand. That is going to be dotted with our differential. Oh, and as we can see, it's too long. There we go. I'm going to have to rewrite this. Yeah, we'll have to rewrite it. Sorry about that. I guess another reason that I labeled this as a more difficult problem, because, you know, I'm having difficulty putting it on the screen. There we go. D phi d theta. Okay, so setting it up, we might as well just go ahead and simplify this. We could sure try. All right, we have sine phi cosine theta times sine squared phi cosine theta. So it looks like we are going to have sine cubed of phi times cosine squared of theta That is our first term. Our second term is going to be sine phi sine theta times sine squared of phi sine theta. So that's going to be sine cubed of phi. And if you guys are seeing what I'm seeing here, looks like we can go ahead and do our favorite identity. I guess we'll save that for a little bit. And then we're going to have cosine phi times sine phi cosine phi. So it's going to be sine phi cosine squared of phi. D phi d theta. Notice if we factor out that sine cubed of phi right there, well, that cosine squared of theta plus sine squared of theta just goes to 1. So we can just simplify that. That is going to be sine cubed phi, and then that's just going to go to 1. And then we're going to have plus sine phi cosine squared of phi, d phi d theta. Anything else I can do here? Oh, I guess so. I can pull out a sine phi from both. Sine phi sine squared of phi plus cosine squared of phi. That's going to turn to 1. Therefore, pretty simply, actually, simplified all the way, this is just going to turn into sine phi d theta. And that is our final integral for our harder example. Note, I guess I kind of did that part in my head. Well, outward flux, meaning we need our values here to be positive. And I guess that's kind of seen here. So we have positive, positive, and then another positive, meaning it will be outward. So I guess I didn't verbalize that check there. So maybe that wasn't the best demonstration, but that differential does indeed conform to our outward flux requirement. So that was surface integrals. Thank you very much.